Okay, now for an optimization word problem. Okay, I have two adjacent fields that are to be made with 800 feet of fencing. What dimensions would maximize the area? Well, first step is to have a diagram. This diagram might lead to a good variable. So if I've got two adjacent and equal fields, now I need to give them a variable. So how about width and length, or x and y if you like. I happen to like w and l a bit. And you don't have to do this all the time. I'm peppering my diagram everywhere with a w and an l. Now in optimization problems, the best technique is to find the term that you're trying to optimize. Here we want to maximize area. So I want to write an equation in terms of area, which is a dependent variable, based on the independent variables that are given in our diagram. So the area of this shape is w plus w, so 2w times length, which would be the area of the rectangle. So 2lw. Now I notice that my primary equation, and that's what we're going to call this, is a primary equation, has two independent variables. In order for me to solve this, I need to get rid of one of those independent variables by substituting for one of them. Now I need another equation to link L and W. So I'm going to look at the 800 feet of fencing. I haven't used that piece of information yet. So how would I spread around the 800 feet of fencing? Well, there are 4 W's and 3 L's. So 4W plus 3L is equal to 800. So that's how I'm going to use my fencing. Now, for this, I am then going to solve for one of these variables and substitute it in. Now, 800 doesn't divide by 3 evenly. It divides by 4 pretty evenly, so I'm going to solve for W. So 4W is equal to 800 minus 3L, and then divide by 4. W is equal to 200 minus 3/4 L. Now I take this and I substitute it in for W all the way up here. So my area is going to equal 2 times length times 200 minus 3/4 of my length. Okay, I'm going to distribute this, so I get A equals 2L times 200 is 400L, minus 2 times 3/4 is 3/2, and L times L is L squared. I'm going to put this in a much more familiar form, just by reordering. A equals negative 3/2 L squared plus 400 L. Now, if we take a look at this diagram, if I were to graph this with area and length, my independent variable versus my dependent variable, this would be a downwards parabola. That's because of the negative. And it would go through the origin, and it would land somewhere out here in the first quadrant. But it'll look like that. It'll be a parabola. And the parabola will have a vertex that is a maximum, which is what we're looking for, maximum. It will have a maximum height, that is area, at the x-coordinate of this vertex. Now the x-coordinate of the vertex is negative b over 2a, and that's the L. The b and the a come from the standard equation of a parabola. So my optimum length is going to be at negative b, so negative 400, all over 2 times negative 3/2. So that equals negative 400 over negative 3, which is equal to, well, let's just leave it as 400 thirds, or 133.3 repeating. And that would be feet. Now that's the optimum dimension for length. Now for width, I already have a nice equation for what my best width should be. So width is equal to 200 minus 3/4 I'm going to use the 400 over 3 here. 400 over 3. Now 3's cancel, the 4's cancel, so this is just 100. 200 minus 100. So my optimum width is equal to 100 feet. So the optimum dimensions for each corral are 100 feet by 133.3 repeating feet.